Also worth noting that the nth root of x to the power of m is the same as the nth root of x to the power of m inside the square root. Okay, so the square root of 16 cubed is the same as the square root of 16 cubed inside the square root. Let's prove it. 4 cubed is equal to, we're proving it now, So the square root of 16 is 4 cubed is 4 by 4 by 4, and the square root of 16 cubed is the same as the square root of 16 by 16 by 16. So 4 by 4 by 4 is the square root of 4096. 4 by 4 times 4 times 4 is 64, and the square root of 4096 is 64. So that's proving that this is the same as that. Okay, that rule holds true. Okay, so what kind of problems do we meet with these? I'll give you two examples here, and I'll state the rule underneath as we're working through them. Solve 1 over 8 to the power of minus 2 over 3. Well, that is the same as 1 over 8 to the power of plus 2 over 3, because I'm working with turning this a to the minus n into 1 over a to the plus n. So here's my a to the minus n, and I'm turning that into 1 over all of that. Okay, and that's the same as 1 over, I'm going to use this rule here now, a to the mn is the nth root, the cubed root of the value all squared. Okay, and the cubed root of 8 is 2, 2 squared is 4, so that's the same as 1 over 4, which is the same as 1 over 1 times 4 over 1. The answer is 4. Okay, what about this one? Solve 1 over 125 to the minus 2 over 3. So that's the same as 1 over 125 to the plus 2 over 3, using the same rule again, which is the same as 1 over the cubed root of 125 all squared, which is implying this rule again, and that's equal to 1 over 25, all of that. So we've 1 over 25, so the answer is 25. Why is that? 1 over 25, so it's 1 over 1 times. We go from division to multiply, but we invert them. 25 over 1 is equal to 25. Now, let's look at expressing numbers with powers. So express 8 as 2 to the power of n. So I have to turn this 8 somehow into 2 to the power of something. So 8 in terms of 2, well 2 times 2 times 2 is 8. That's 2 cubed, so that's 2 to the power of n. So 8 expressed as 2 to the n is 2 cubed. What about express root 2 as 2 to the n? Well, root 2 is the same as 2 to a half, because that's going from the nth root of the value equals the value to the power of 1 over the n. Okay, the nth root of the value, the square root of 2 is equal to 2 to the power of 1 over that. Okay, so we've expressed this in terms of 2 to the something. The n in this case is a half. What about this square root of 8 is 2 to the n? Well, that's square root of 8 is the same as the square root of 2 cubed, and so we've learned earlier in the video that that's the same as the square root of 2 all cubed, which is the same as 2 to the m over n. Okay, but the first thing we're doing always is turn the 8 into the 2, or the 8 into the 2, or whatever it is we're looking to change. Okay, but that's where this bit comes from here. So they do take a bit of looking at these, but it's kind of by practice that you start to get into the swing of them. Okay, express square root of 32 as 2 to the n. Square root of 32 is the same as square root of 2 to the 5. That's the same as the square root of 2 all to the power of 5, which again is an m x to the m situation. And the 5 goes there, and the 2 is there, and this 2 is there. Root 8 over 2, well, that's the same as 2 to the power of 3 over 2, because we did that earlier, over 2 to the 1. So that's the same as 2 by 3 to the power of 2 minus 1, 2 to the power of a half. 1 half minus 1 is a half. So you can see with that one, that this one built from earlier solutions. let's look at equations involving indices. The rule is if a to the power of x is equal to a to the power of y, if two things are the same here, same base, then x must be equal to y. So 4 to the x is equal to 16. Now to employ this law, I have to turn this into the same base, turn it into a 4. So 16 is 4 squared. So now I have 4x equals 4 to the 2. My 4's are the same, so this x must be equal to this y, x is equal to 2. And in fact, yes it is. If that 2 there, 4 squared is 16. What about 16x is equal to 64, so I need to look for some common base number. Well, I know 4 goes in there and 4 goes in there because 4 squared is 16, so I can just write it like that and leave the x outside. And 64 is the same as 4 cubed. So now 4 squared all to the power of x is the same as 4 to the 2x, 4 cubed. So now my 4's are the same. I can pull down my 2x is equal to 3, x is equal to 1.5. Okay, 3 to the power of x equals 1 over 27. So I need to get this in terms of 3. That's 3 cubed. So 3 to the power of x is the same as 1 over 3 cubed. 3 to the power of x is the same as 3 to the minus 3 when I bring that up. And 3, if that's the case, my 3's are the same. X is equal to minus 3. And of course this comes from the fact that a to the minus n equals 1 over a to the n, in the other way around. Okay, example 4. 25 to the power of x equals 1 over 25. So let's get both of these in terms of 5. 5 squared is 25. The x is the same as 1 over 5 to the power of 3. So 5 to the power of 2 of x is 1 to the 5 over 3. So 5 to the 2x is 5 to the minus 3. Same rule being applied here. So 2x is equal to minus 3 because these 5's are the same. X is equal to minus 3 over 2. Express 81 over root 3 as a power of 3 and solve 3 to the power of x minus 2 is equal to 81 over root 3 all squared. Okay, what is 81 over root 3? Well, let's get it in terms of 3's, top and bottom. 81 is 3 to the power of 4. Root 3 is the same as 3 to a half. So that's 3 to the power of 4 minus the half. It's 3 to the power of 3 and a half, that's 3 to the power of 7 over 2. 2 3's are 6 and 1 is 7 over 2. So 81 over root 3 squared is at 3 to the power of 7 over 2 squared, which is 2 times 7. 3 to the power of 14 over 2 is 3 to the power of 7. Okay, and now we need to solve this equation here. So okay, so we go up to here, and we say 3 to the power of x minus 2 is equal to the original equation. So 3 to the power of x minus 2 is equal to 3 to the power of 7, which we worked out earlier below. So that means that that's the same base. So x is equal to y, x minus 2 is equal to 7, x is equal to 9. Okay, let's talk about surds, but let's start by talking about perfect squares. Okay, the square root of 1 is 1, it's exact. Of 4 is 2, of 9 is 3, 16 is 4, square root of 25 is 5. They're exact numbers, they're perfect squares. Okay, these numbers are known as perfect squares. Root 25 is a perfect square. What about non-perfect squares? So the square root of 2 is this big long never-ending, non-repeating number. The square root of 3 is this never-ending, non-repeating. Root 5 is the same. And these are irrational numbers. They're never-ending, non-repeating. These guys are perfect squares. Okay? So this root 3 and root 5, they're known as surds. Okay? Their value is an irrational, non-ending, non-repeating number. Okay? So these are surds, these are perfect squares. The value of a surd gives an irrational number which is a non-ending, non-repeating number, goes on forever. You can't. It's irrational. And just another thing to note then as well is that with numbers, numbers have two parts. Or these surds, they have two parts. But numbers have two parts. They have an irrational part. Well, there's two parts to this number here. There's root 5. Root 5. There's two parts to it. It has an irrational part, which is the root 5. And it's the part we never see, the 1. That's the rational part of that number. We'll be meeting with the fact that these numbers have two parts, irrational parts and rational parts, in the next video.